Hello, everyone. Welcome back to my channel that's dedicated to unraveling the mysteries and stories of the past. One big question I've always wondered about: how pristine was the environment around us before modern industry, industrialization, and pollution screwed up everything? Like acid rain, heavy metal emissions, microplastics. They really do seem overwhelming now. But we have to remember that decades ago, scientists began sounding the alarm on many of these problems. And this led to the awareness of the issue, and regulations like the Clean Air Act were passed to tackle some of these contaminants. But have any of these regulations actually worked? Can we assess how well they have worked? Is the environment truly getting better, or is it just wishful thinking? So to dive deeper into this topic, I've invited scientists Skylar Hooler and Aubrey Hillman to discuss their groundbreaking new study, 5 decades after the Clean Air Act, legacy metal contaminants in Northeast U.S. surface waters document full recovery for the first time. Their findings might surprise you. Metal pollution in many lakes have decreased since the 1980s, but what is behind this recovery? Is it stricter environmental regulations? Or is it the decline of local industry due to globalization? Or is it a combination of both? So let's get into this. What do you think? Is it the regulations? Is it the economy, Sky? Or do you think it's a combination of both? Can you argue one way or the other for this decline in metals that you're finding, metal deposition in these lakes in the Adirondack Mountains in New York? Can it be explained by regulations?
I think it can be explained by good regulation,
Okay.
such as the Clean Air Act.
Okay. And
So,
what do you mean by good regulation?
regulation that actually has an impact. Even though it might take a long time, it's clear that this was good regulation, it worked, and this is the first paper to find that that is the case, even though it was very slow.
Okay. Aubrey.
So, I tend to agree. And I initially remember when we saw the results, I was pretty surprised. And I also remember thinking, well, can we really attribute this to the Clean Air Act? Like, how do we know that that is the reason? But Sky and I worked through the data, and we developed good estimates of age deposition and when the metals start to decline. It was clear that the timing is very tightly correlated to Clean Air Act enactment and then further amendment and regulation, right? So it got even stricter a couple decades later. And there's such a clear connection in timing between those things at all of the lakes that's I think that the connection is really striking.
So that's like almost the smoking gun. The timing is just so perfect. And so for the people that are watching that may not be familiar with the Clean Air Act, it was first passed in 1970 in the United States. And then it was strengthened in 1977 and 1990. And this was basically the regulation. What it does is it limits air pollution. I wrote it down, sets air quality standards, protects health, and targets major threats. And it mainly works through the regulatory agency known as the EPA, the Environmental Protection Agency. That's where much of its enforcement comes through. And since then, at least public estimates or estimates available on Google say that it cut 70% of pollution since 1970 through those regulations alone. Okay, so it's this temporal correspondence. So in the lake cores, you analyze metals through time. So let's step back and just look at these lakes. What is lake coring exactly? How did you estimate background metals? How did you estimate modern fluxes? And then this return to natural conditions. So let's start there. What are the 3 sites you actually looked at? The 3 lakes. Describe like briefly maybe their watersheds, where they are at, and their history around them. Like, were they near mines? Are they logged? Are they pristine by today's standards, like old growth forests, etc.? And then we'll get into, once we describe the background, let's then talk about the field work you did there, dating, etc., and we'll move on from there. So yeah, whoever wants to take that, let's talk about the background of the 3 sites, the 3 lakes.
Sky definitely knows that more off the top of her head than I do.
So Sky, go ahead.
Yep. So it is quite a pile of collecting like historical data to come to these stories of each of the lakes. We used many resources and maps, for example, and just talking to people around the area to kind of get together these stories. So they might be a little bit incomplete, but they're definitely the best that we could get to at this point. So we actually worked with 4 lakes in this study. We did start with looking at several, but there's various reasons that those were not included in this paper. So our favorite lake, I would say, is Chalice Pond because it's considered a heritage lake. It's a reference lake that we use because it has had very minimal human impact on it.
Okay.
It's surrounded by old growth, supposedly.
Mm-hmm.
However, there's speculation when looking into older maps that maybe there was a fire that took place before the 1900s. But Chalice is surrounded, however, starting around the 8th, in a little pocket of mining activity when we looked at historical mining maps. And we do not know the extent or magnitude of these mines and the processing of the material, but we can say that this area of the Adirondacks was probably more highly impacted than the other regions of this mining. And then there are the lakes, which are located kind of near Lake Placid, Rat, Black, and Little Hope. And these have been impacted by a much greater magnitude from humans. And we know that Rat was impacted by logging, and it might have been slightly acidified, nothing drastic, because that's difficult to tell what its natural pH was before humans moved in. So we can say like maybe a little bit. And then Black Pond, 50% of the watershed was impacted by logging. And then the other 50% did have a massive fire on it. And Little Hope Pond, our 4th one, was highly acidified. And that had its own issues of mixing of the sediment with big storms that came through, however. So that did derail the timeline a little bit for us.
Okay, so you have a range of watershed disturbances in the modern, let's say. It sounds like you go from Chalice, which is about as pristine as you're going to get for Adirondacks, to Little Hope, which is acidified. And you say acidify, that means through acid rain deposition, and it's pH, the pH of the water, the lake watershed's poorly buffered, so the pH can change to more acidic conditions.
Yeah.
Okay. And it doesn't have like acid mine drainage going directly into any of these lakes, though, like straight from the creek.
No, these lakes, I forgot to mention, are not developed watersheds. So they do not have like housing developments on them. And if it is, it might be like one house. There is, however, some modern day development possibly on Black Pond. We're not sure to like how this has impacted it. We do make some theories within the paper of what we think is happening there. And Rat Pond, it has also this historical railroad going along one of the sides, but it's difficult to tell how much this has impacted it. So we classify these lakes' impacts basically into the major disturbances on the watersheds.
Mm-hmm. Okay. So today they're mostly, forested. To like a person that's out there, it seemed like they're undeveloped, like a regular, not thinking of geology. Okay.
Mm-hmm.
And would you say, hydrologically speaking, are they closed basins? Do they have streams perennial streams coming out of them, going into them, any of these lakes, or all of them?
So they do vary by lake, and I include a table in the supplementary of
Okay.
like which ones are being fed and which ones aren't. I think, can you recall, Aubrey, which ones were being fed?
Chalice, I think, is rainwater fed only, right?
Okay.
It does have a outflowing creek. Black, I know for sure, has inflowing and outflowing streams. I also think Rat. I can't remember about Little Hope, though. That's the one I can't recall.
Okay.
I'm going to go ahead and pull up the supplement to look at.
Yeah.
I'll pull that up on the screen too as you're doing that. So it sounds like Chalice is going to be, really sensitive to atmospheric, especially if it's just rainwater fed. That's usually how geologists, we look at that. Just, not that having an open basin won't record modern pollution. That's certainly not the case, but, it's nice knowing the only things going in are rainwater, and maybe the only things coming out are evaporation, ideally, but a little bit of overflow is not a big deal either. And they're all what we consider smallish lakes, Aubrey, like, 10 acres or something.
Yeah, I would say Black Pond is the only one that's maybe a slightly bigger, but even that is still relatively small compared to a lot of the lakes that I've worked on. And Chalice in particular is quite small.
Okay. A small lake.
So we did
Sky.
choose the lakes based off of their watershed area to surface area ratio to keep it standardized.
Wow. Nice.
Yeah, we
As
have
much
to.
as possible, it's a little difficult, but we did the best we could. Yeah, keep it around, was it 10-ish?
Yeah, yeah.
So that means, like, if it's a 1 acre lake, the watershed's 10 acres, taking out the surface area of the lake. Wow. Aubrey, it's like you're a professional. Did you get your PhD in this or
Can you
something?
believe it? Sometimes I kind of know what I'm doing. It's amazing.
So depth wise, are they about the same depth too?
They range from 6 meters to about 14 meters.
Okay. Yeah. Those are good depths too. You don't want them too shallow. You don't want them drying out. Are the bottom waters oxygenated or any of them? What's the
Yeah,
water
this is an
chemistry?
excellent question.
Sky, can you tell us about these lakes?
That's touching a little on my other paper, which I'm working on right now.
Nice.
And I would conclude just off of that data that these are pretty low oxygenated bottoms. So
Okay.
it varies by each lake, but yeah, it's not looking very healthy, I would say.
Okay. And you have a hydrolab or a multi-parameter sonde that you guys,
Yeah,
you
some of the
use?
data is a little wonky, but
Yeah, those things are always, you got to
yeah.
calibrate them every time, I feel like.
Yeah. But Sky, you should mention it, the Chalice at when we went most recently. Was that last summer?
Yeah. Yeah. So when we cored it most recently, last summer, we actually found the presence of purple sulfur bacteria. Yeah. And this is supposed to be our healthy lake.
Yeah.
So do you think that's a recent occurrence? The purple
Yeah.
sulfurs are recent?
I think there's been some drastic changes in the last couple of years to this ecosystem.
When we cored it in 2021,
there were no
sulfur
purples.
bacteria. And we cored it in multiple locations in 2021, right? So it was not like this isolated.
Yeah. And we can see a crazy shift in the data too, not just.
Was it a drier year before the purples that like led to something like concentrating?
No, it was actually a wetter year.
It was a wetter year.
Yeah.
And you mentioned the purples we found in the West, Aubrey, right? Yeah, and those are in dry, semi-arid, super alkaline lakes. Is Chalice alkaline? Or is it like soft water? Is it hard water or soft water? Like a Marl Lake? No carbonates? Yes. What the heck? There's purples in a non-carbonate lake, but it has a anoxic hypolimnion.
Yeah. Sky has a really great picture that she should send to you of the bacteria when we pulled up the surface core. You can see it's a really striking picture.
And they're bright purple, right? That's how they are. Yeah, it's amazing. We had like a side project, I think Byron worked on it with Bill Gilhooly. I don't know whatever ended up happening with that, but that's something that I think, Aubrey, keep that place in mind, because there are people that are interested in that kind of stuff. Like, and now with this DNA work, you could do some DNA on that. And where do these purples come from? Like, they just show up when the conditions are right. They're like inert spores until the conditions are right, and then they just
That's
come
what
alive.
I was wondering. Yeah, do they like go into like a hibernation, for lack of a better word, right? And then like the conditions are right, and then they just suddenly like thrive.
And the bottom water is acidic. It's anoxic and acidic, and there are purples in there. And that means there must be a sulfur source. And is this a lake that is infected by salt on the road?
I don't think so. I think it's too far from the roads, nearby roads, and it's not even within the.
Okay.
It's vicinity to run in there.
Are any of these lakes near a road that is? Do any of them have watersheds that are actively being salted in any way?
I would say the only one that could be possibly is Little Hope, because there is a road that runs along one side. However, it's not a highly used road.
It's like a dirt road.
It's a dirt road, yeah.
Yeah, so it's probably not salted too much.
What about Black Pond? What do you think about that? Because that runs right by Paul Smith's college.
So I think that could affect that region where you put in the boat, but I doubt that it's making it that far, because that lake is pretty large and pretty long. Yeah, part of it would be affected, but not the area that we're looking at, I don't think.
It seems fair.
Okay, so we have lakes that are pretty comparable, small lakes, all in the Adirondacks. I'll have a map, put it up, and they are kind of lower on the pH scale, or at least poorly buffered, maybe we can say. They're not alkaline water. And I define alkaline as greater than 100 milligrams per liter of dissolved carbonate bicarbonates. That's stuff that we did with the titration. And that seems to hold up. When you get around 100 or even high 90s, you'd start to see carbonates in the sediments. But so that would kind of mess also with the geochemistry of the lake, because I noticed the sediment, because you did an acid extraction, and that would certainly take up carbonates, but there's no carbonates, so we don't have to talk about that. Now, you go there, you found these great sites. They're all the same size, relatively undisturbed. Then how did you figure out how many metals were in the lake before industrialization, which I'm saying is like the advent of fossil fuel use in the mid-19th century, and then, during the peak, which I think remember is like around the 1970s, 50s to the 70s or something, and then this decline? How did you do that? What did you sample from the lake? Can you describe what you did at those sites?
So something that we did, which was a little bit different than other studies in the area, is that we really wanted to look very far back before humans to get that really good image of what the natural environment did look like in terms of metal concentrations.
Okay.
So
you went way back in time. How far did the records go in these lakes?
So they went back a couple thousand years. We actually had one which goes back to 6,000. I do not show that much data in the paper. That's just too much.
Yeah.
But it's open source data, though.
Okay, so you have thousands of years of sedimentary layers analyzed from all four of these lakes. It varies from, what's the shortest?
So let me go to my little supplementary. It's hard to remember these details here, but I have a figure that shows iron and manganese ratios. One moment. While I pull that up.
I and Sky have poked around the Adirondacks now for so many years and poked so many lakes. It's hard to keep them all straight.
Yeah.
You have no idea. We have probably like two to three times more what's in the paper as like cores that are sitting. But I open all of my cores. None are unopened.
Nice.
All right, so I've got the data.
Okay.
So Black Pond goes back 500 CE to 500 CE. So that's our shortest core.
That's the shortest core. So 500 CE gives us that's about 1,500-ish years. And then the longest one is 6,000 years. And you analyze metals for the whole cores, right? Even though if you didn't show them in the paper.
Yeah, we did stop the data collection at some point because we were like, we just don't need this.
Yeah. Okay. So you did your due diligence in establishing what you would consider background or natural fluxes of metals in the lake. And what were the metals that you looked at in these lakes? I think I even wrote them down if you don't remember. Let me see. Or maybe I didn't. No, I didn't.
It's okay.
There
I
was,
can go through them.
yeah, there was a bunch of metals. That was pretty nice.
Yeah, so we actually analyzed for a lot more than we also show within this paper, but we just chose just for the fact of we need to keep this paper kind of condensed within the limits. It's already at the highest limit that the publisher would allow. So we analyzed and put in this paper arsenic, manganese, zinc, lead, cadmium, nickel, cobalt, chromium, copper, and iron, because we felt those were the most relevant.
Okay. Those
I think we run
great.
in total a suite of about 30 now is what we've been running pretty well on an ICP OES.
On the OES, yep. Nice. Cool. And then you're doing, I thought I saw nitric acid extracts. Are you doing full bottle strength or are you doing the 1 molar?
So we do a weak extraction of it because this is what we think represents that anthropogenic bound metal.
Nice. And that's that grainy citation. I know what you're doing. So that's what Aubrey and I did back in our PhDs. So yeah, we did like 1 molar nitric extract or 10% or something. And that seems to be, I've dug into this a little bit more working with soil scientists here because we're trying to do like extracts. And it does seem like the nitric does liberate or dissolve the heavy metal fractions well. So it's representative of what's actually in this sediment. A lot of other extracts just don't target that. And there's reasons why that is. It's not like a big mystery, but so nitric is good to see. So we have nitric extract and ICPs, a top of the line, inductively coupled plasma spectrometer. And it's ICP OES is inductively coupled plasma spectrometer, optical emissions spectroscopy. Yeah. So it's probably up there. I think MS might be a little bit for like ppb levels. But we're looking at ppb being part per billion. And all the concentrations I saw reported in your paper we're looking in the part per million range, right? For almost all of them, well within the analytical capabilities of an ICP OES. Because sometimes you'll see atomic absorption, AAS, I don't even know, something like that. That was back in the day. And then you'll see XRF, which is okay, but not as good as ICP. Okay, so we have top of the line analytical equipment, modern extraction, ultra pure nitric extraction I remember seeing in the paper. And then you say you got 6,000 years or 1,500 years of sedimentary layers. Now, how did you get those sedimentary layers from the lakes? Yeah.
So Adirondacks, their cores have very high water content. So instead of keeping together the cores how you usually would in sampling, we actually chop them up into 0.5 centimeter intervals, all of the sediment.
In the field?
So we do the top part in the field and we transport once it gets a little bit less watery and it's just more compact and it's going to stabilize. Then we take that back to the lab and chop that up because it takes a long time.
Yeah. How far did you typically extrude in the field?
We usually go about 40 centimeters before it gets a little bit more compact.
Yeah. Sounds about right for those lakes. And would you characterize them as like organic, rich, fine grain, or sandy, or?
Not sandy. They're basically relatively the same, pretty high organic matter.
And probably, similar to mini cores I worked on, like boring, brown, homogeneous, doesn't look very exciting.
Except for
on the face of it.
A little red, though, at Little Hope. Little redness.
Little redness.
That was the most exciting one to see.
Oh, okay, so that got a little red after you pulled it out? Did it like oxidize red? Because that's your acidic lake too.
No, actually, well, we think that this is because of a storm that took place there where it was oxygenated.
Oh, so it's a distinct red layer.
Mm-hmm.
Ah, cool.
Yeah.
Okay, so you have organic rich homogeneous sediment. So that organic matter and that fine grained sediment, those are great for sorbing to particulates like aerosols from industrial emissions that fall from the water, fall from precipitation or dry fall onto the lake. They get absorbed by this sediment, incorporated into the lake bottom, and they essentially are, like, would you say, like a record of emissions to that body, that watershed through time, like kind of like reading a record keeping type of record keeping. That's all it
Book,
is,
Mhm.
of
a
pollution.
newspaper. Yeah.
Yeah, almost like like a newspaper over time of these environmental changes. And so what kind of were these cores? How would you describe the cores? Were they like freeze cores? Were they in metal tubes? Did you use plastic tubes? How did you do this? How deep were they, or how long were the cores?
So the tops of the lakes that, we need a lot of that sediment because it's just very high water content. We got a lot of those with this method that I really enjoy. It's the gravity driven core, and it just kind of drops into the lake bed and suctions. This one I do find a little bit easier for quick grab of like a lot of sediment. But for that deeper sediment, we used our typical Livingston cores and a push method.
Mm-hmm.
And they're about a meter long each. And we got, I think, as deep as we could go at most of them, just kind of kept going until you couldn't go anymore.
And in the case of Black Pond, this is the one where I had carbon fiber rods made by Jason Curtis, top of the line, amazing. And then the coupling at the end of the rod broke.
Just
The
broke.
whole thing went down, and we were holding the Livingston and like 5 or 6 carbon fiber rods on the line, the metal line, and we had to reel it up with the Bruce reel, like millimeter by millimeter. And it took hours, and it came up, and the whole thing was saved.
Wow, except for
So
that little coupling.
I thought for sure I've lost everything. The whole thing came back up. And then I later talked to Jason Curtis, and he said, "Oh yeah, that was a batch that I had where the glue was really bad." And he was like, "Real sorry about that. I'm glad you didn't lose anything." But
Wow.
I think that was only 3 or 4 meters down. But so we were lucky. We were very lucky. But that, I think, was probably about the deepest we got on that lake. I didn't want to push my luck.
Yeah, it's like you always, you prepare for these coring trips and then something goes wrong. It's like comes out of nowhere, or like you get tangled in something. You're like, well, I can't get the cable untangled. Like, what the heck's going on? Or I just forgot the coupler or the saran wrap when you're about to do an extruding. I remember just that one time, and you're like anchored and everything, and someone's like holding the core, and you're like, I don't have any wrap. Like, well, paddle back. And you're out there, for people that have never cored, you're doing it by you're blowing up 2 rafts or taking canoes, and you're paddling yourself, anchoring. This is all a hand-driven operation. There's no motors.
And I should note too that in the Adirondacks, can be really challenging because the roads do not go to the lakes. So for Chalice, we had to hike everything in, it's about 3/4 of a mile
Wow. Yeah, and that's heavy
uphill.
equipment.
And then Little Hope, we had to push through some pretty big branches. Yeah, it was not easy.
Rat Pond. Rat Pond is a nightmare.
Rat is also a nightmare. Yeah, so this was it's not a trivial operation. We don't just pull up to the lake. We often have to haul the gear quite a ways because many of these lakes, and in fact, many of the ones I wanted to core, we just couldn't get to. It was just absolutely impossible.
Wow. Even in the Adirondacks, you'd think that they would have
Especially
nice,
in the Adirondacks.
especially. Do they do this
Because
on
they don't,
purpose?
yes, forever wild. And so the DEC leaves it underdeveloped. And they have the state has very strict rules about what can be developed under what land classification. And so, like, even the hiking trails, in Adirondacks, they don't do switchbacks because that would cause too much disturbance. Trails just go straight up the roads. So, some of them are just impossible to get to, and the DEC leaves it that way. That's the way they want it.
So I'm glad they're doing that to protect the lakes, because I know a lot of them, like especially near the Syracuse area, are really affected by the salting of the roads, and they're becoming permanently meromictic. And the bottom waters, they don't ever overturn because of the salt, the saline density differential between the top and bottom water because of the salt in the roads. So that's, I think, is imperative to keep the roads at bay around, especially those small, really freshwater lakes, for that reason alone, really. And it reminds me of a story of coring, like maybe not losing everything, but almost losing it, was coring Lily Lake on Isle Royal. And it had like 8 meters of brown sediment in it. We took out with the Livingston 1 meter at a time and took the top. And this is a lake that's on Isle Royal. It's like 3-mile hike. 2 of it is bushwhacking through the woods. And it took us like a day just to get everything up there with like 5-6 people. But we got the whole Holocene, and we started to see the glacial sediment at the bottom. And I guess Byron's like, you know what? While we're here, we might as well, we don't need the glacial sediment. Let's just get a glacial, see if we can get a core down there. And it's like now, so 10 meters down, puts the Livingston in, and this thing is stuck in the glacial sediment. Like, it's like a plug. It's totally a vacuum. And we have all these people, nobody can pull it out. It gets to the point where they literally never done this before. And I've never done it, but left the whole Livingston, had to just stay in the lake overnight with the rods and the boat, and like had to come back and haul this huge metal truck jack that had a thing that you could tie to the freaking rods, and then we put it on the boats and then use the truck jack, just jack, and the whole buoyancy of the boat pushing down to push up and hold it. And it slowly inched it and popped it out of that clay. And otherwise, it ate one of the Leathermans, went down into the muck. I guess maybe I shouldn't say that maybe I'll edit that out. They know about it though. We told them that the parks, because we had to bring the truck jack up there because it was like, can't get the core. It's like, we're going to have to be leaving the Livingston in that lake if it doesn't come out. And they're like, yeah, take everything up there. But anyway, we got it. And that's just one of the examples of everything was going well, 3-mile hike, 10 meters of mud, or, 8 meters of brown mud. And then the last core of the day plugged.
It's always
we're
something.
talking, that equipment's like $10,000, $15,000. So it's not trivial to lose that, especially when you're in a national park and it's in a pristine lake.
And all of our equipment is tagged too, right? So the university then comes around next year. It says, "Where is it?" I'm like, "Oops."
That happened to be very far away right now. Okay, so you got these cores. You brought them back to the lake. And when we say cores, it's like a straw pushed in the bottom of the lake, kind of, and the layers are in there. And it's like, I always tell people, it's like pushing the straw in a slushy, and then putting your finger on the slushy straw, and you pull it out, and you have that core of the slushy. And within that core, it's containing those layers that record, like the newspaper, bookkeeping, all the inputs to that lake over the course of the time that sediment was deposited. It could be year, decade, so on and so forth. How, and you looked at it every half a centimeter, it sounds like, and maybe half a centimeter to a centimeter. How did you determine the age of those layers? You just have depth, right? How did you know how old the layers were?
Yeah, it's always a common question from people who aren't familiar with this field, because it's very very
Mysterious,
mystical,
almost.
mysterious.
Yeah, it's mystical.
Yeah. So for the upper section, we use lead 210 dating, and for the later sediment, we use radiocarbon.
Okay, lead 210. Do you use any cesium?
We do. Yep. We match it with the cesium peak.
137. And what was the cesium peak again? Tell us what that's from.
So that's from the atomic bomb.
Yeah, the maximum atomic bomb testing 63 to 64 on the surface, which was banned that year, I think 64 to 65. And globally,
Yeah,
cesium
crazy.
declined because I personally have detected cesium peaks from 1963 in lakes from Sawtooth, it's 79 degrees north, and Tasmania.
Really?
Yes. And then all in between the mid latitudes. But I remember, and Svalbard at 78 degrees north.
I do remember. I remember you finding it at Sawtooth because I remember that was notable. Thought one of the
And
highest lakes.
yeah, it's like, so 90 degrees north is literally the geographic North Pole. So we're finding cesium across the world. And then that declines in 64, 63, 64. So we can use that layer, that enrichment of cesium to date the tops of pores. So that's what you did. And you use that to verify lead-210, which is another radionuclide that we use to date because it has a shorter half-life of about 22 years. And so it's useful for dating the upper 100 years of sediment or so. And your lakes, how far back was it, like your lead-210? Was it like the top 20 centimeters, 30 centimeters roughly?
Yeah, about 30 centimeters, I would say, before you hit those background levels.
Background levels. And then after that, below those depths, then you use radiocarbon, which is C14 or carbon 14, the isotope that decays after every 5,000. Do you remember, Aubrey? 5,180 something? 84?
It was 5,280. So
Roughly
crazy.
around 5,000 years. We'll double check that. We'll see who'll put it up. But yeah,
Yep.
so that one is useful for dating like especially the last 10,000 years, but it can go back as far as 50,000 years at its very extreme. But you're focused on the last 6,000 to 1,500 years. And how many radiocarbon dates did you use? If you have it available over your 4 sites, how many dates?
So for each lake, our goal, I would say, is to have a date every 500 years for the longer records. So I can't say for the exact number. We're always building up on it as we develop the age models. So for these, I wouldn't say that was like a big goal of the paper was to have a very well defined set age model as you would with other studies because
Hello, everyone. I just want to take a moment to ask you to please subscribe to my channel and like this video to support science communication. Check out this amazing beach behind me. Let's do this.
what we're interested in is just to know, even if the cores aren't lining up exactly, the average of that background metal concentration. So this wasn't something that was like crucial for this study, but definitely
Right.
that top section and a little bit past that, we definitely wanted to have a very accurate date on.
Yeah, that makes sense. And I think, having the radiocarbon dates at least assures us that the sediments that you're determining your background conditions are at least, dated to before that big influx of big change in the landscape, which was really the 1800s probably in New York. We'll get into that. So that's actually a good
Yeah.
segue. So up in the top part of the core then, where the timing of the layers is really important, which would be the last 200 years, you're using this combination of dating approaches of lead-210 and cesium-137 with a little bit of the tail end of the radiocarbon. So you have multiple dating methods that you're cross-referencing to assure us that
Yeah.
those layers that you're analyzing and telling us the metals about are dated, in fact, to that period.
Yeah.
Okay. So when do you first see metals start to elevate above natural baseline conditions in the Adirondacks?
So this changes by lake, but
Okay.
I would say generally between 1900s and the 1940.
Really? 1900s or 1940? I
Yeah,
always
that's
say
when it's like significant enrichment.
that's a significant.
Yeah.
Okay. I like that. And let's get into that a little bit. But like, okay, so then when you see it though, like first tick up a little bit,
So for that, we
roughly.
had to use change point detection because it's so subjective.
Yeah,
At what
yeah.
point do we surpass that? And that does change by lake. I believe Chalice Pond was the earliest that we saw, surprisingly, for it being this unimpacted lake. And that starts sometime in the 1800s, I would say around, let me see for the exact date that it was. Earliest enrichments in zinc in 1849. It was very subtle. And then for the rest of the metals, it was 1905 that it started.
Okay, that's interesting. My experiences in this field, I've looked at Horseshoe Lake in the Midwest, Avery Lake, Midwest, and the Michigan Copper District Lakes. And I didn't do the significant change point analysis, but the metals start going up in the Midwest like in the early 1800s, definitely by the mid 1850s. Like at Horseshoe Lake, which I was just looking at with the new age model. Thank you, Aubrey.
Mm-hmm.
It's 1810, but I know down there, Horseshoe Lake's by the Missouri lead districts where the colonial people made musket balls, and it's documented in the literature. I mean, it's written in the Little House in the Prairie.
That's
The
cool.
guy used to smelt little musket balls at his cabin. Like people had small scale lead smelters. The French brought them in to make stuff, and my guess is that's why or could be mixing. But the reason I think that you're on it, like there's something here going on is, you look at the lake in Western Pennsylvania, the one we worked on with Rob, where it was actually had an age model at the top of the core.
Markle. Yep.
Yeah. That had a later increase. Like it was like late 1800s, 1900s there. And that's Pittsburgh,
Yeah.
like outside of Pittsburgh. And, so it's so strange. Are we really seeing an earlier lead pollution signal in the heartland, like St. Louis area, and up in New York? It's like later, and even Western Pennsylvania, or are we just seeing? Is this just like a function of the geochemistry of the lakes and mixing
I've thought
age
a lot about
models?
this because, we've thought about a lot of this in the context of the Adirondacks, but I think for that initial period, I think what you're getting is like a very localized signal.
Yeah.
And then it's only as industrialization spreads and you have sort of a high enough magnitude of volatilization of metals that you actually start to see it become meaningfully transported to the Adirondacks. And so maybe it's that at Chalice, for example, right, it's very close to this localized signal, whereas at Rat or Little Hope, there isn't a local signal until all of a sudden there's more of like a regional signal.
Okay. I see what you're saying. Until there's a regional signal, because for all four of these, like what's like the nearest smelter, let's say, or something big industrial like emission type place. Do you have any or have a feeling of any of that?
Chalice
Well,
definitely has one. Chalice is the
yeah.
closest, right?
Yeah, it's the closest, but we don't know the magnitude of the industry around it. So that's the limitation. But we know that they existed and that it's just in a pocket of it. I think it does get affected early on because of those early industries, those little increases. But yeah, like Aubrey said, the larger increase, it does correlate very well with the lead consumption in the US, such as the coal and the leaded gasoline consumption.
Yeah.
When
Okay.
you plot that against sort of national data, it lines up
Yeah.
really nicely.
Okay. So say that again. So you're saying when you plot the metals from the lakes, that lines up better with lead emissions from gasoline than anything else?
Yeah, we actually combine the data to correlate it with our metals, especially very interested in lead.
Yeah,
And we
lead.
looked at historical US coal combustion and leaded gasoline consumption in the US, and we find a very high correlation with these concentrations.
Okay, I see exactly. Yeah. So you're seeing This makes sense then, because if you're seeing significant, what'd you call it, change point increases, that's your statistical test, not until the early 20th century, between 1910 and 1940. And that makes sense, because when did they add lead to gasoline? Sky, do you know this? You should have known this. It should be part of your dissertation. When did they add lead to gasoline? This is your committee. You remember? Without
No.
Googling it.
Let me look up the particular year, because I don't.
Okay.
I'm going to need a cheat. Hold on.
And then when did they ban it?
That's a great question. I really should know that. My assumption was with the Clean Air Act, honestly. I figured it was it was tied in there.
Definitely is tied in there.
Okay. So it says it began in the 1920s that it was first added as a fuel additive.
Yep, an anti-knock agent, tetrayl ethyl leaded gasoline. All it does is make your engine run cleaner. It runs quieter.
Yeah.
So we poisoned everybody in America to drive quieter cars. It lit that sediment, and it emitted the most bioavailable, toxic form of a heavy metal and sprayed it on everybody and their kids' little brains. I mean, that's what happened. And it wasn't make the car run quieter.
Yep.
And so, that was introduced the mid 1927 or 25. But it doesn't become widespread really until the growth of the automobile. So the Great Depression, I think, hampered it a lot. But when it spread, especially with the advent of the vehicle, the suburbs, the 50s and the post-World War II era. And it wasn't until 1977 with the second strengthening of the Clean Air Act that it was started to phase out, and it was phased out entirely by So if you're
you're telling me we're the first generation to have been born in a lead-free America? Well,
or at least the atmosphere probably was way less than definitely 10 years before we were born. In 77, when they phased it out, everyone was just breathing in, especially if you lived in a car dense area, like, you would have just been breathing it in. And in fact, like, I'm sure Aubrey and I have talked about this back in our office in the days, but if you look at blood lead concentrations in kindergartners, they have records of that from the 60s and 70s. They make the kids from the Flint, Michigan look like nothing, except for the really bad ones from Flint. Because I did one day try to check. There's some really crazy ones at Flint where like the kids are through the roof and they have like a direct poison. But overall, everybody and the kids in that they have this blood lead levels, and it's done by Rick Nevin. He was a researcher that published or at least compiled the data from the 60s and 70s and stuff. Everybody had elevated lead pollution. So to see that you had major increases at your lakes from 1910 to 1940 makes total sense. So that's like another verification that you're actually, because 1920s it's added in, but it still has to, it's a brand new technology, leaded gasoline at that point. So it's got to spread. And then by the 40s, 50s, we're in full-blown post-World War II expansion. And especially cars are taking Americans to the rural areas and back in ways that never happened before, like camping, car camping. It's crazy to think that that's a new thing. Like before you like had to get your carriage and your horses and stuff and like go for weeks. It's like, now you can go car camping, and that took you to places like Chalice Pond and other things like that, and logging technologies and trucks and other things like this. So crazy to think that they have all this smelting, Pittsburgh for iron industry, steel. I don't know what else is going on up there. I'm sure tons of industry in the late 1800s is active all throughout upstate New York. I mean, that's when that area peaked in its economic.
Yeah, it's booming.
It's booming up there, but it's still not, because it's still leaded gasoline apparently. But that only explains lead. Let's get into this. So lead seems to go up that time, but you also see, from what I remember, your other metals like cadmium and other heavy metals also go up. Can that be explained by leaded gasoline, or is that something else, or is that a global signal maybe?
I'd say that there's a lot of metals that are being introduced into the atmosphere at that time from coal combustion and other industries.
Oh yeah, coal, that's it. So coal is going to explain the other suite, the array of heavy metals, because there's just a bunch of stuff in coal.
Mm-hmm.
Yeah, trace metal, especially sulfur. And I know you tracked, this is a big, sulfur emissions was a big change during the industrialization of the world because it created acid rain, the famous acid rain, which is, on a technical sense, it lowers the pH of precipitation. And it's because of the addition of sulfur and sulfuric acid, its production in the atmosphere from these emissions. And I think in your paper, you go into, don't you think this is a strong driver of some of your changes in your metals is the sulfur and its reduction of that sulfur and that acidifying force? Like, does that contribute to this reduction in metals, you think, in the recent times?
One of the things we've thought a lot about is when you have acid rain falling on the lake, not only does it change the water chemistry, but it also is falling on the watershed. And so that also changes the availability of things like free aluminum. And then you start to change basically what else can be complexed in the soil, right? As you acidify it. And so that also releases some of these heavy metals that would be otherwise bound. And then that, I think, that washes into the lake, and that also contributes some of what we see to the increase in metals in some of the lakes, at least.
Okay. So in addition to lead, excuse me, what are the other metals strongly correlated with the lead curve in the modern that like kind of track pollution along with lead that might reflect coal?
So for coal, it would be aluminum, manganese, iron, cadmium, zinc, nickel, copper, etc.
Okay.
Arsenic.
Arsenic, yeah.
Arsenic.
And those are all strongly correlated with that lead signature too. Because I think I saw your table of correlation coefficients.
Yeah.
So it seems to be all like kind of tracking the same atmospheric sources.
Yeah, it was really interesting to see like which ones were correlated before humans and how that changed after humans.
Okay, tell us a little bit about that. What was a change you saw, that something that stood out?
So the big change was the naturally correlated metals, which are being input from the watershed before humans. That included iron, manganese, zinc, and copper. They had very high correlations. And then that completely changed after humans started disrupting the metal deposition. And that switched to very high correlations of lead and arsenic with all of the other metals, which just didn't exist before.
Whoa. That's an interesting test. I like that.
Mm-hmm.
This thing, yeah, these correlations through time. Because one way to
really
think about,
shows.
one way to think about humans is that, especially when it comes to metals, is, and I guess now exploring other things like carbon isotopes, is that they seem to preferentially emit certain things, certain elements outside the range of natural variability in the watershed. And so that is really like the smoking gun of human activity, is that we have all these suite of natural processes that act on these lakes. Weather phenomenon, every once in a while, big downpours, snow, El Niños, forest fires, what have you, herbivore extinctions and new introductions of species through changing climate over the Holocene. The processes that drive these metals, they go far outside the range of those forcings, because you could see it in the core. And that's kind of what you're saying, is these processes vary and they show this natural variability and erosion. And we could go into the fine details of that. Some of our colleagues are very interested in natural processes. But when we're looking at these pollution signals, they're non-stationary. They fall far outside the range of the standard deviation and mean of the natural process. That includes that range. Like I'm saying, like we can throw it all in there. El Niños, droughts, weather, hurricanes, fires, and they just don't seem to do it. They don't seem to drive fluxes of heavy metals outside of their ranges of natural variability. So it's just it's strong evidence that what we're looking at in these lake cores are, in fact, accurate records, extremely, I would say, accurate records of heavy metal fluxes to the environment through time. And they're not influenced by politics. They don't care about industry. They don't care about lobbyists. It's not an activist in any way. It's just telling us what actually happened, and what we do with that information is the important part. And I think just investigating whether or not these regulations are working is already a hard enough question to do without getting tripped up with everything in politics and that. And so we need some kind of, let's say, independent record that's standing on the sidelines to tell us stuff.
And
Now,
Dave,
the
you
interest,
may be aware of this, but part of the initial investigation into Adirondack lakes, the paleoecological assessment of lake acidification in North America, something, I forget the exact term of the acronym, but the reason that that was undertaken was because there were lobbyists, politicians who said, well, how do you know that this trend in acidification isn't just natural, right? I mean, it could be that like the lakes are just acidifying themselves. And so John Small and other colleagues, Don Charles, Kurt Steger, a lot of those, when they looked at these lakes in the 70s and the 80s and looked at the diatom assemblage changes, that was specifically to show that over thousands of years, this trend in acidification was absolutely not natural, right? And it was, it's amazing that like the playbook is always the same. Right?
yeah,
It doesn't
it's
matter.
always the same. And that reminds me of the Claire Patterson story with the lead pollution
Mhm.
in the air. And Claire Patterson, the most famous and important scientist that most people have never heard of. And that's actually a title, an article online.
Yeah,
It's,
that's right.
yeah, it's just amazing. He discovered, by trying to date the age of the Earth with using uranium lead dating, he discovered that his samples were contaminated, which led to a lifelong mission to uncover and eliminate lead pollution from his lab and the world. And it is nothing short of legendary. And he was like, in the beginning, that he said the same thing. He's like, there's a lot of lead in the environment around us in California, and it seems to be way higher than normal. And the industry's like, no, that's normal, natural lead all around you. And this is like the 60s. So this is the peak of leaded gas. You're like in California just spraying everybody. And yeah, he kept getting bad numbers on his lead uranium dates. And he realized, holy crap, my whole lab is contaminated. My hair, my skin cells, my everything. So he created the clean lab. And then he went and proved everyone that the lead around the environment in the 60s was way, way above average. He looked at, one of the interesting studies I remember was looking at mummies. And
Oh,
then,
really? I didn't know he did
yeah,
that.
he analyzed teeth concentrations, I think teeth and bone. He did lead to calcium. So he ratioed them to see lead above calcium levels to affect, to, maybe to account for changes through time. And what he analyzed modern teeth from Americans and British people, and then he analyzed mummy teeth and bones from Egypt and Peru, like thousands of years ago, these people's teeth. And he showed that modern teeth were like thousands of times elevated over the Peruvian mummies and lead in their teeth. And we know our teeth form like in the early part of our life, especially our adult teeth in our jaw. And it would literally, it's like capturing your blood lead level at that moment. And your teeth, you remember, is made of apatite, not collagen. So your teeth are like a mineral and they're a lot more stable. And so he showed right there, like, holy crap, like are talking people are through the roof with lead. He also did ice cores from Greenland. He did sediment cores from the ocean. As a result of his work and talking with people, and I don't know how far he went with government and stuff, They eventually passed the Strengthening of the Clean Air Act and everything to remove lead, and from soldering on food cans, water pipes. It was literally like we were soldering our tomato soup, our acidic tomato soup in Campbell cans with lead up until like the 70s. Yeah. And we all know, the other famous story is the Roman period. Are we seeing, like, at least in the present, some of the older generations around us, are they crazy because they were on lead? Do we sense that somehow? Is this comparable to what we felt the Romans in their later stages, where their elites were drinking tons of leaded wine? I mean, imagine how crazy you are drunk and hungover, let alone drunk, hungover, and you're drinking lead.
I always love that story because it just sounds so fantastical, but it's true, right? Like, if you don't have an understanding of toxicology, like, yeah, why not, right? Lead tastes
and
sweet,
it was sweet. It's
supposedly,
sweet.
right?
Yeah, it was sweet taste. Then you hear the emperor got paranoid and murdered his cousin,
Yeah.
and then married the horse. And you're like,
Yeah.
how much wine was that guy drinking with lead? And then you're like, oh, now this all makes sense.
Yeah.
All these stories of them going berserk and like impaling people, and like they're just like in their little like castle, like swigging this stuff down. There's no aspirin. You're mad. And the being lead poisoned is exactly, it brings out symptoms of, basically, it turns you into a criminal because it lowers your IQ, it makes you more impulsive, it makes you more emotional, it affects your frontal lobe, which is your executive decision making. It makes it harder for you to understand the implications of your actions. And it also makes it harder for you to perceive emotions in other people, to empathize with them. So think about that hard when you know someone that grew up with a lot of leaded gas around them. They may not actually physically see the world biologically the same as other people if that lead legacy contamination is still in their brain. And we know if you're affected by lead when you're a kid, it affects you your whole life. It has a lot less of an impact when your brain is formed and you're exposed to lead versus when your brain is forming. It's a lifelong affliction after that, which makes it so much more dangerous to put in leaded gas to make a car run quiet. Before, we had the leaded paint problem, which is it is a problem, especially when you're a baby and you eat dirt, which, makes it available in your, acidic stomach. But otherwise, leaded paint is like nothing compared to leaded gasoline, because it's still, you have to disturb it to make it, sand it down without a respirator on, or have your kid eat it somehow, or it's stuck in the garden dirt of your tomato plants and you ate it like that. We already had that issue, and then we added the leaded gasoline on top of it. It affects so much of a person's behavior that it's disturbing. And when they actually looked at records from the leaded gasoline plants that actually created this compound to add the gasoline in like New Jersey, it's just horrific. The companies knew that people could only last so long working there before they went crazy.
Really?
Yeah. There's stories of people jumping out the window, stories of people thinking like stuff is flying after them. You hallucinate and you become violent. It's really, really, it's terrifying stuff. And that was in the 20s and 30s. Those were the leaded gasoline plants. They knew. The powers that be that run Washington, and the lobbyists and everything that influenced everybody, they knew for a fact that lead was bad for people, and they still did it anyway. But the good news is we put those Clean Air Act in, which, based on the timing, you're saying it's not just the decline in the industry. It's like, in the late 80s and stuff, we shipped our jobs overseas, as they say, a lot. And I do think there is some bit of that, especially in the places I grew up, like Western Pennsylvania, for the decline in industry it just was not competitive globally, especially when we changed the like NAFTA and everything. And maybe that I sometimes think, that would have just naturally reduced emissions just because you have less industry and it didn't really have to regulate. But the regulation sometimes made the industry not profitable.
Right. Yeah,
because you have to put,
it's chicken and egg scenario in
yeah,
some
so it's
ways.
like you
Yeah.
put the regulation in, no longer can I just sit there and pump zinc into this neighborhood. So now I need to go and do this in another country where they look the other way.
Right, exactly. I can go do this in China where, nobody
Yeah,
will.
nobody's going to regulate me. And then it's like, then we attribute that to the Clean Air Act, which it is, I guess, maybe then directly a part of it. But what I want to get into is this recovery, because it's remarkable. I mean, this is I think, an amazing story in a sea of negativity sometimes, because wow, since the 60s, from the 60s to 90s, like the metals seem to peak in these Adirondack lakes, and they are coming back down fast, really fast. In some of the lakes, right, Sky, they're almost natural. They're back to almost their pre-industrial conditions, or pretty close to that, right?
Yeah, for many metals, it's close to that background level again. And for some, it's as close as we think it's going to get right now.
Okay. And I guess, it's only maybe going to get better. I saw the trajectories and all of them are down. So they're going to hit to some kind of natural level and kind of bottom out, hopefully.
Maybe or maybe not. It really depends on what's still floating around the atmosphere.
Mm.
There is still some lead in the atmosphere that's going to be contributing to it. So I don't know if we'll ever get to as low as levels as there was previously. But this is as far as we can get, and it's really low. So that is like the optimistic point of this, is that it's not still running as like hopefully legacy metal into the lake environment still. So that's
Okay, so
greater
lead, you're
than
saying
90%.
it's greater than 90% recovery.
Mm-hmm. Yeah, for
Okay,
all of them, definitely. Yeah.
I like those numbers, greater than 90%. Now, the lead, though, so maybe if you have a table available, and maybe choose two good examples, give us the background lead, the peak lead, and then the most recent sample lead, to give us a little perspective here. Maybe pick the worst and the best one or something.
So, well, we look at it as flux. There's two
Or
ways of looking at
flux.
it, flux or concentrations, but I think
And describe
concentrations.
what are the
What
difference?
flux? Okay, yeah. That's the concentrations is just the pure concentration of the metal within each of the samples, but we corrected and normalize the amount for the depositional environment of the lake. So this is realistically how much is within each layer based on the density of the sediment and the sedimentation rate.
Nice. Okay. That's awesome. So you counted for that. Density changes, sed rates, everything.
And that's like the standard way to look at it in these kinds of long-term studies, to compare and see those trends in enrichment, peaks, and reduction. But for concentrations first, I would like to talk about these were the most astounding things to us, from those background concentrations to the peak concentrations. We were definitely not expecting the results regarding these high concentrations. So background lead concentrations at Chalice Pond specifically were about, I think, 3 ppm. And that's the average of those very long-term records. The peak was 131 ppm. And this is pretty astounding for a watershed that hasn't been affected at all by anything. That's just direct deposition.
When was that peak? 131.
So the peak, we do like to look at flux.
Oh, yeah, flux.
And that is for lead specifically. It's in 1970. I have to look at the exact year. I have to reference my paper.
Okay. Yeah. In 1970s.
Yeah.
Sounds about right.
It was the 1970s. I'm forgetting which year, but it was right in that window that we would expect. Mm-hmm. And then we see it tapering off slowly after. And that taper off really trends very well with the sulfur dioxide reduction as well in the atmosphere. And we got this data from the local Whiteface mountain stations and Huntington Wildlife. Yeah. And now onto the higher impacted lakes.
So Chalice, what is it at in the most recent sample?
So the most
For
recent sample of
ppm and
concentrations, I don't have that data up right now, but
even
it
if you
does.
eyeball your graph, what is it on the graph?
So for flux, it reduces 92% from background levels in the current day.
It decreases 92% from the peak to
Yeah,
background levels.
Yeah, from those
Okay.
background levels to the peak back to the modern day sample.
Okay. So we're in 1970, it peaked and it's declined 92%. Is what you're saying, right? Okay.
Yep.
And that's in the lead flux.
Yeah. The other metals.
Which is a good, yeah, I like lead flux. I know you did a bunch.
Yeah.
But it's better. It's one of the cleanest of the metals to analyze. And as Aubrey would say, without getting too much into it, it's stable in the sediments, not really that sensitive to redox. Yeah, stable with organic matter and clays. And
it's really held in the watershed for a long time. So it's like if that has recovered, the other ones have recovered more. And this is just the slowest one to recover out of, I would think, all of them that we looked at. Okay.
And then what was the other one you're going to say?
So all the other metals, I mean, at Chalice, they're greater than 92%. Now, moving on.
Okay. Yeah.
So moving on to the more disturbed, like highly disturbed lakes, such as Rat Pond and Black Pond. Rat Pond was really crazy because there are other studies that have found like very high enrichment in lead concentrations in the lake environment. But this surpassed those other studies that are quite rare, and we weren't expecting to find something so detrimental, I guess. So this one actually rose from 3 ppm to 328 ppm at the peak. At Rat.
3 ppm to 328 ppm. At what time is that peak?
So that peak also lands around 1970. Yeah.
It's 1970. There it is. And then it's got a 90% decline or greater since 1970?
Yeah, this one had a 94.7% decline.
Surprisingly, like that's the lake that I envisioned to have been the most polluted and yet has recovered almost the best.
Yeah.
328 to down 90%. So that's triple the peak concentration of Chalice in the same size lake, essentially. The watershed.
Yeah.
Okay. Very interesting. And then what was Black for background and peak?
So Black is 4 ppm for background and 295 ppm for peak. Oh, wait. Yes, I think that's Black. Yes, that's Black.
Okay. So another near, a little under 300. And sorry, did you just say what was the timing of that peak at Black?
So the timing of that one is around the 1970s as well. I can't say for sure without looking like in depth in the paper exact year, but
I'm sure it's quite similar to all of them because that really to me was why I was like, this is the reason, right? We can attribute this is because the timing is synchronous at all of them.
Yeah, that is amazing. So 1970, we know, car camping, driving around the highway, suburbia, full on, everybody is coal combustion, leaded gasoline is at full. What is our nearest coal plant to the lakes? Did you look that up? Is it still in operation or did they close it down? Okay.
I thought it was over in Canada. I could be wrong, though.
So their laws are a little bit different than ours, and they had continued emitting after we had reduced ours by a great amount. So, yeah.
Yeah, I can't recall exactly. I want to say the nearest coal-fired power plant was in Canada, but I could be wrong. I could be thinking of something else. Aside from that, I'm not really sure. In the U.S., I'm not sure.
Okay.
I do know we looked into that at some point.
Because I know they may not have shut it down, but they probably put scrubbers and they put tech to keep like a lot of the sulfur, a lot of the mercury down. And that probably had a huge impact. Because I know in Kansas, there was still, when I lived in Owego, there was a big coal plant and they had added all kinds of scrubbers and stuff to it. Wow. So you went from, yeah, I don't even think that's like on the level. I think that's even higher than when I see at Horseshoe Lake.
Yeah, we checked.
Did you check?
Because, yeah, Horseshoe is the one, like, my one reference point of, like, wow, this lake was
Yeah. Because
really
it's right
bad.
next to literally a lead smelter. It's on the shoreline, a modern, full-on smelter.
Yeah. So
The
I was
zinc,
like, this is my reference point, right? And so
yeah,
I can't remember exactly what it is at Horseshoe, but I remember it's higher, and I was shocked.
it was so high.
Yeah.
And zinc is like so high at Horseshoe Lake that it's on percentages. It's like, it's not even part per million anymore. It's like thousands of part per million. And yeah, I'm seeing if I can pull up the lead real quick to see if I can just look.
I can't remember.
Because it
I also
was
want to say that, well, this is in
200.
South America, but yeah, there you go.
Even at Horseshoe Lake, it's only 200. So 200 part per million. And it looks like the 200 part per million at Horseshoe Lake, which is at St. Louis, just to reiterate, that is 1970. Oh my gosh.
Wow.
Raiden, that's the Bacon age model. Yep. That's the new age model. 1970.
Nice. There you
median
go.
age 1970. I'm not rounding it up or down or anything.
Nice.
So we just validated independently with another core your findings, and the cores don't lie. The cores are the cores. They're just layers that we've analyzed through time. It's like a little mini time machine.
It is.
That's what like brought me like fascinated to this subject was things through time, how they've changed through time. I don't know why. I guess Aubrey, you probably have the same interest as me. I don't like it. Just fascinates me.
It blew my mind when someone first introduced me to the concept of lake coring, because I was like, wow, you mean like we can reconstruct the past? Like, that's amazing. Like, I had never heard of anything to do with tree cores or ocean cores, much less lake sediments, and then I was just like, wow, that is amazing that we can do that.
Yeah, and especially when you start to see it work with like you get a new core, you do an age model, then it like matches what you found at a lake independently, and you're like, holy crap, this thing's really recording something real. Like I did it, and it's like I didn't rely on anyone else, and like this is what happened, and I can't believe it. It's like they really work, and that's like when I found that, like I found these lead spikes from Native American copper mining. And man, they're all over the Michigan Copper District, and we've done it in multiple labs, and it's there. It's like remarkable.
Reproducible.
It's reproducible, and it's like maybe someone will find out another reason for those lead spikes, and they'll be able to explain it. But they're there. You cannot deny that there is a non-stationary, rapid increase, preferentially lead above other metrics of natural weathering in those lakes. In the modern and in this prehistoric time, and the radiocarbon dates match up with the copper mining activity that we know happened there. But the thing that got me really interested in this subject was learning about the green Sahara and it turning into the dry Sahara, and it blew dust off the continent of Africa into the Atlantic Ocean, and they cored sediments off the coast of Africa, and they found all this iron dust blows there when the Sahara dries out. And I was like, I didn't know about the green Sahara. I was like, holy crap, that changed and you can record it. To me, that was really crazy. Yeah.
So we didn't even believe what we had found. So we were like, there has to be a mistake. So we literally went and we had new cores, and we ran the samples again on these new cores and found exactly those concentrations again too. And they were like perfect replications.
Wow. And you had, I saw your co-author, William Kenny. He did the lead 210 with his modified CRS, which seems to be working nicely, apparently.
Yeah. And he uses a hybrid model now.
Yeah, it's hybrid model. Aubrey and I talked a little bit briefly about that when we were in Liverpool, but I still would like to see more eventually. Maybe we'll run some lead 210 eventually.
Yeah.
I would
You
like
should
them to
ask
do
him.
it.
Because he has a very in-depth understanding of how these, like, he's thought a lot about the math behind it, and he's clearly onto something. I couldn't explain it all to you, but he clearly he's thought deeply about how to best modify the CRS model and really pinpoint ages with a higher degree, or I should say a lower degree of 2 sigma error ranges, basically.
Mm-hmm. And for those listening, when we say CRS, that's constant rate of supply lead 210 model. It's a way of interpreting the exponential decay in lead 210 relative to radon 226 and its daughter product lead 214, which are stable through time in the radon levels. So you basically want to see when does lead 210 become equal to the concentration of the background, more or less. And that takes about 4 or 5 half-lives, or about 80 to 100 years. And the other lead 210 model that no one really uses is the CIC model, constant initial concentration. And then you use that and you interpret from that initial concentration, what's the half of that, what's the, another half-life, and then you're able to put in ages for that. But that doesn't account for density, sedimentation rates, and whatever William has figured out. Interpolating between those dates, which is also kind of hard because he really takes a lot of time to get one date per gamma spectrometry. Is that what he's using, by the way? Yeah, it's like 24 to 48 hours a count. So it's not trivial to do one sample. And you need it's an expensive machine. And so you have solid dating and this peak in metals in the 70s. And it seems like basically a 90% or greater decline since that time. And it's remarkable because Clean Air Act, when was the first law passed? 1970, when we see that literal shit is hitting the fan geochemically. And your lakes, Horseshoe Lake near St. Louis, and I'm sure many other lakes around the US and in the world. Yeah, pretty crazy. Any projects lined up, Skylar? What's your next move?
So the next move is the second paper, which
Okay.
is also based in the Adirondack lakes. And it actually uses a lot of, these same lakes, but has an addition of a couple more within the data set, comparing these lakes, which have been impacted by varying degrees by humans, to assess the ecological changes. So we looked at the pollution changes. Now it's more productivity, nutrients, the trophic state. And these results have been really good, been very astounding as well, but not such a positive conclusion as this paper has been.
Yeah, maybe, not such an uplifting story of environmental rebound and resilience.
Yeah.
But maybe there's this little glimmer of hope in there somewhere.
Yeah, we traded off one problem for another problem, and
the purple sulfurs, which is an interesting problem. What are you going to do with those? Aubrey, have you thought about reaching out or doing something with?
I haven't really thought about it, mostly because I was waiting on Sky to kind of get the chlorophyll data, but it's sky high chlorophyll concentrations, right? Is that right?
So it was like an algal bloom at the time you were at the lake?
No.
No?
Wasn't like a visible algal bloom. Didn't look clean, but nothing crazy.
What was happening? When did you core these lakes? I guess did we talk about? I don't think we mentioned that.
Most of them were done in May and June over a series of 4 or 5 years.
So last 10, but since 2020, 2018.
Yeah,
okay.
2020, 21, 22,
that's when it
23,
started.
24, yeah.
But It's been following throughout the years. Just go back, get more, and extend them.
Yeah, there's so many lakes there.
I'm going back in a week.
Yeah.
Yeah.
I want to check Chalice for microcystin to see if that very toxic algae is present. Because
harmful
this is
algal blooms.
Yeah, this is a spot that people really like to go fishing at. And I mean, that's very impactful. Very unhealthy to be exposed to. I mean, I went swimming in the lake. I feel kind of gross about it now after seeing it.
Did you swim in the lakes after you cored them?
Yeah, sometimes because it gets really
Yeah.
hot and you get really dirty. You have to wash off.
And you're on a boat already. It's like, hey, might as well jump in. Mostly.
Chalice
Sometimes
and
they're scary.
black. I think I swam in black. It was, but maybe that was accidental to get the sacrifice myself for the sake of the equipment. Yeah.
Did you jump in to grab something?
I think I did. Yeah.
Nice. That means you're in all the way. It is paleolimnology, which this field is the field work is very physically intensive and it's dirty and you have to have good patience with other people. And yeah, because you're oftentimes put in situations that you're on a little boat in a windy raft and you're just like squeezed in with all these people and you have to be patient while you're all moving, so many moving parts. But it's what I call type 2 fun, because at the time, sometimes it is fun when you're doing it if you're well rested and maybe.
And you're working with good people.
Yeah.
I had to quote Mark Brenner, who once told me a long time ago that his best colleagues were his friends and his best friends were his colleagues. And I was like, yeah, I kind of agree with that. That's my perspective on a lot of it too.
Yeah. There's something about having a really good colleague and a friend.
Yeah.
Like you, Aubrey, for me.
Exactly. That's what I'm saying. Right? Like you and I have done so many coring expeditions, like, you know, so many things. Yeah, it's hard work, but you know what?
Yeah.
It's fun. Like you can't beat being outside on a day like this and just like hanging out and getting some good mud. I mean,
the best feeling is too, you know, because I'm in Hawaii now, as you know, but when the winter finally breaks and spring hits and field season's on and you like finally school's done and you're just like getting your field gear ready and you're ready to go out to the wilderness and it's like June, it's the best feeling. It's
That's
like,
right.
Oh, yes. And then you come back, it's like July 4th and you're relaxed a little bit. And I'm doing a little bit of that coming up in June, but I'm not. Yeah, like I mentioned, I'm doing some stuff in Michigan. For the people that don't know, Aubrey and I were in grad school together at University of Pittsburgh, and we were office mates for basically the entire time. Mm-hmm. And so we talked a lot about each other's research. Sometimes I remember your research just as good as mine because we looked at each other's graphs in our office over and over again and trying to like just get our papers moving forward and every day trying to like, you know, like
bang our heads against the wall.
Yeah. As because science moves too slow for us. We like to move at a very fast rate.
That's right.
Which is just try to publish papers. Yeah.
This is a 16-year friendship, Dave. That's pretty long.
Yeah, man, that is. Yeah, we're getting there. We're getting up there now, Aubrey. We're gonna be.
Tell you.
Can't believe it. Getting older. It's like time doesn't stop for us either. Yeah. Anyway, so I guess also in the beginning, I just was thinking earlier, I didn't properly say where you both work. I mentioned you're both scientists, but I do want to say, Aubrey, this is Dr. Aubrey Hillman, and you work University of Albany. Are you associate or assistant professor?
I'm still waiting on the president to sign my tenure letter, but once that's done, I will be associate professor.
So yeah, assistant, soon to be associate professor if everything goes well, and I'm sure it will. And Skylar, you are all but dissertation. You are working on your PhD. This subject we talked about today was part of your PhD dissertation, or is part, and you're aiming to finish. You have a rough idea?
Yeah, definitely by December graduation. So get everything written up by then and submitted.
By December 2025.
Mm-hmm.
Nice. Awesome. You're almost there. Keep it up. Don't give up at the end. Keep getting those papers out. It'll be nice to look back on it and you'll see you have all these nice papers published from that and they're there forever. So
yeah, it's been rewarding so far. And the response to this paper has been really nice and encouraging, just like the public's response. Not just scientists.
That's your first paper too.
That's your first paper. Congratulations.
It's been a long time coming.
I saw the press release and I'm like, Aubrey Hillman's in there. And then I'm like, what the heck? So I had to look through it. I'm like, what? And so I pulled up the paper and I'm like, this will be perfect for the channel because it's really a combination of geology and history and human society, economics. I love all that stuff. Like that's what this channel is about, is like improving the communication of scientists. Let's let them make their voice heard. We don't have to hear it through podcasters that don't talk to the real scientists. Let's hear it from the scientists themselves. There's a lot of interesting stuff coming out, and we can barely get our colleagues to read our papers, let alone the public.
Yeah.
So we're publishing papers
I know.
like it's Isaac Newton in like the 1700s and this like proceedings of this academy. And when it's so easy just to talk about your results, I do think they'll never replace true writing of a paper just as a concrete record of the results to be referenced. But we have other media today that we can control better to get our message out there from our own mouth. So yeah, and if you enjoyed this conversation, please like, subscribe to my channel. I really need subscribers because I have a lot of people coming back to watch the videos, but not everyone is subscribing. And I would really appreciate it if you could get the subscriptions up. It helps the algorithm and helps my videos reach new people that are interested in the subject, and hopefully the end goal being better science communication and a more informed public, and in a format that we can all, kids to adults, can take in and learn something from. So thank you so much, Sky. And thank you so much, Aubrey, for coming onto my channel. I really, really appreciate it. It was an amazing conversation. Aubrey, maybe you and I will cross paths this summer. I'll keep you in the loop if I drive across New York. I don't know if you'll be doing field work. That'll be a better excuse.
I'm going to be here. Oh, but yeah, you could also, I mean, an excuse to come like camp in the Adirondacks. I'm always like, is this field work or is this like a vacation?
Yeah. All right. Okay. Until then, Sky, good luck with everything. Aubrey, we will see each other soon.
Yes, absolutely.